Testing 1, 2. So just carrying on this videos on the design of reinforced concrete column sections. I wanted to do this part as quickly as possible because I realised that I never really understood how these charts, reinforcement charts, work. The charts that you get in BS8110. So they're basically interaction diagrams. So the basis of the interaction diagram is on the x-axis. This is actually section 3.5 of the presentation that following on from video number 1, but I wanted to skip to this because this is the most important point, so I want to get this out as quickly as possible. So 3.5, this is a design of short brace column for moment and axial force. So it says for a range of values of x over h, a set of points results, each representing a combination of axial force and moment. Any combination of applied moment and axial force that fall inside the curve is therefore safe against failure. A number of important points can be identified in a typical interaction diagram as indicated. So on the y-axis of this interaction diagram, you have axial force N, and NUZ is the crushing. Remember, we've looked at NUZ. That is the crushing load capacity of the concrete column section without any bending moment. So see my video part 2. That's described in there. So on this interaction diagram, basically what it's given you is the safe capacity of the column with axial load and bending moment. So you've got stresses added together. I'll do another video, part 4, I think, on how you work out the stresses. You've got compression from the axial force, and then you've got a bending moment, which is a little bit of, it could be a little bit of compression or a little bit of tension. But say, for example, you might have this section is half in compression and half in tension. So then you add that to the axial force, and that gives you the overall stresses in this section. But I'll go over that in more detail in another video. I just wanted to get onto this interaction diagram. So this is like charts BS8110. Got design charts for actual beams as well, for beams and columns, but specifically beams for this example. So on the bottom axis you've got bending moment M. And on this line, that's where it says point B, where it's parallel to the x-axis, that end balance, that's where this section is failing in tension and compression. So that is the greatest, the point B is the greatest capacity in bending moment and compression. So at the top, so I'll just read that out again. So this is section 3.5, description of interaction diagram. So for a range of values of x over h, and x is the depth to the neutral axis. So for a range of values of depth of neutral axis, x divided by h, depth of the section, a set of point results, each representing a combination of axial force and moment, is obtained and basically plotted like on this interaction diagram. Any combination of applied moment and axial force that fall inside the curve is therefore safe against failure. A number of important points can be identified in a typical interaction diagram as indicated below. So point A here, that is 100% bending moment with no axial force. A, which is pure bending. This point represents that of a beam in bending. It's not actually quite, that sentence isn't quite right, because this point represents that of a beam in bending, pure bending moment, because as far as I know, usually a bending moment, usually a beam is only singly reinforced, whereas a column will always have symmetrical reinforcement. So that first sentence, I think it needs a little tweaking in the description. but in theory it is just a bend. A beam is bending, but you've got reinforcement in both faces, so it's like a doubly reinforced beam. So note that the presence of a small axial force will generally increase the moment capacity of a beam, and that is because it will reduce the amount of tension. So basically, it will move the neutral axis a little bit, and the concrete can take a bit more compression, because in a concrete section you've got a big amount of concrete, unless only bars usually on the bottom in tension. So point B, which is here, there's a little I'm going to go back over this again, and I'll explain the diagrams. I'm going to do them bigger. This is point A here, this is point B, this is where M balances. So that's the I think that is the, here it's got the stress diagram, or is it the strain diagram? Similar, X balance with a strain. So this is the point where the concrete reaches its ultimate strain at the same time the tension reinforcement yields. So this is the point where the concrete reaches its ultimate strain at the same time the tension reinforcement yields. So basically as well, you're saying that the compression, the concrete has an tension failure, so the strain is in compression. For combinations of N and M that fall below the balance point, the failure mode is ductile, with reinforcement yielding before the concrete fails in compression. Otherwise, the failure mode is brittle. The concrete crashes without yielding of the tension reinforcement. Unfortunately, the failure mode in a column cannot be controlled by reinforcement quantities as it can in beams. So, just read the second sentence again. For combinations of N and M, so N and M, that fall below the balance point, that's tension failure, I think. The failure mode is ductile with a reinforcement failure, yeah, so it's tension failure below the N balance line. Otherwise, the failure mode is brittle, i.e. it's failing in compression. The concrete crushes not elastic, basically. When it says brittle, it means not elastic. The concrete crushes without yielding of the tension reinforcement. Unfortunately, the failure mode in a column cannot be controlled by reinforcement quantities as it can in a beam. Pure axial compression. C. Point C on the curves, that's where it's NUZ. At this point, the column is subjected to an axial force only with M equals 0. The capacity of a section is equal to NUZ. Note that the tension reinforcement yields in compression for this case. Point D, here. Point D is 0 strain in the tension reinforcement. Moving from point B to point C, it can be seen that the neutral axis increases from X balance to infinity as N increases. The strain in the tension reinforcement changes from yielding in tension to yielding compression, passing through 0 at point D. Moving from point D to C, the neutral axis will fall outside the section, and the strain will eventually change from triangle to uniform. Between points B and C, an increase in axial load N will lead to a smaller moment capacity M at failure. Conversely, below the balance point, an increase in N will increase the moment capacity of the section. Okay, and point E here. Point E, yielding of the compression reinforcement. As the axial force N increases and the neutral axis increases, strain and compression reinforcement will also change from elastic to yielding. This will clearly be influenced by the strength of reinforcement and its positions within the section. This point will typically correspond to a change in slope of the interaction diagram as shown in point E, which is here. When he says a change of slope, he means the change of gradient. Then it's got a little bit of notes on minimum n. Note 1, all columns can take some small tension, so minimum n. All columns can take some small tension. This may be needed, for example, in a pile that needs to resist uplift. However, you need to be cautious that you do not have a cracking problem at serviceability limit state. Note 2, in many cases you will find that you are in the lower part of the interaction diagram. When this is the case, it is important to note that the most critical case is the minimum value of n combined with maximum coexisting m, i.e. Example, n varies from 100 to 300 kilonewtons, m from 0 to 200 kilonewton meters. The critical case n, m, is 100 to 200. N, and so on this one it's got yy is n, xx is m, range of n with m equals 200.